and rudder parameters, it is very important to concentrate on what rudder is going through when it is traversing a shallow water, restricted water depth. So here in this work, we try to develop a mathematical model, rather a regression model, that would give us a reasonably good prediction of the rudder forces. Rather, we put that in terms of the rudder hydrodynamic derivative, the force and moment hydrodynamic derivatives due to the shallow water effects, by fitting a proper regression curve with different shallow water conditions and what the rudder is going through for various rudder angles. This is done in a mathematical way. I know, being the last speaker, I have a bigger responsibility of engrossing the audience, but unfortunately, I have too many equations, sorry, because the work is on developing a mathematical model. So the figure, if you can see a part of the figure that shows a rudder, that's a previous research work by some of the contributors to the field. It is shown that the rudder, when it is in the slipstream of the propeller, what is the kind of forces or the moments it's undergoing. So this gives a kind of, or at least an indicative idea of what the kind of complexity we have here, and why do we need to consider the rudder hydrodynamics when we traverse through restricted waters. It would be really good if I can have the next slide, full slide. So I would just come to a conclusion of this slide also, saying that this is a status of the present research in the area, where I have come to a conclusion that though there has been a lot of contributions from various contributors in this area, starting from Kijima in the year 1972 to the contributions that are as late as 23 and 24, there has been a lot of considerations for this rudder aspect, but a equation or a prediction which Kijima otherwise gives as a correction for hull in shallow waters is missing for rudder and propellers. But rudder has a bigger contribution in for the maneuverability of the vessel. So there is a requirement for having an empirical relationship that connects the water depth to the span ratio of the rudder, and that could give a good prediction of the rudder derivative in different water depths without even having to model the rudder and do a CFD analysis or an experiment every time you have a different depth coming in. So if we look at the hydrodynamics of rudder, we have this typical maneuvering problem where we have the maneuvering forces developed, and we all know that in maneuvering we follow a northeast down system, and the rudder rotation, which is a clockwise rotation, is considered positive, and for every positive rotation of the rudder we see that there is a hydrodynamic pressure that is created. If the rudder is going from the amidships to the port, there is a net hydrodynamic pressure because of the Bernoulli's equation balance that is acting from the port to the starboard. So a net positive rudder force, a net positive rudder angle, but a net negative rudder moment because the moment here is in the anti-clockwise direction. So if I look at, give you the equation of this sway and yaw in maneuvering, we have some hydrodynamic derivatives. Some of the hydrodynamic derivatives were introduced by my NSTL friend, Rahul Kumar. But I would like to give a manifestation of this hydrodynamic derivatives, which is very important from my work point of view. There is a YV dot that comes and gets added or subtracted with mass, which is manifested as an added mass component. And there is a YV velocity dependent derivative that is manifested as a damping coefficient. And on the other side, we have Y delta. And similarly, we have NR dot coming, and that is getting added with the mass moment of inertia. And that is supposed to be the added mass moment of inertia. And NV, a coupled derivative in yaw, and n are the your velocity dependent derivative in yaw, and n delta is the rudder moment derivative. So y delta delta r gives the rudder force, and n delta delta r gives the rudder moment. And what is required in maneuvering is the two coefficients y delta and n delta. So we restrict our focus to y delta and also n delta. That is very important for us in maneuvering, and we see their variations with varying water depth in the upcoming slides. So if you look at the forces acting on the rudder, in the direction of the flow we have drag, and in the perpendicular direction of flow we have lift. Of course, opposite to the direction of flow we have drag, and in the perpendicular direction we have the lift. And this is how the y delta delta r, the rudder force, is determined theoretically. And it is, to make the problem simpler, it is understood that the rudder moment derivative n delta can be a function of y delta. So we further confine our focus, or we narrow our focus to y delta, that is the rudder force derivative, that makes the study a little more simpler. So this is a spade rectangular rudder considered, and this is the configuration of water depth that is shown in the figure. So we take the depth, that is the depth coming from the load line or the draft line of the hull indicatively, and the span of the rudder is taken as the denominator, and we find this ratio of water depths, and to these water depths we try to figure out what are the different rudder forces, and directly, and from them we fit curves to extract y delta, and from y delta we fit a curve for various water depths to get a regression fit that gives a ready-made value of a rudder derivative for any water depth. So we had to consider very shallow water with a very narrow under rudder clearance to deep water case, which give us a wide range of values, or a more number of values, so that the curve fit becomes easier and more accurate and more reliable. So we go for the CFD method, because a conventional or the experimental method seems to be impossible for this number of experiments or the number of simulations we do. So we go for the CFD method because it is easier for us to initially understand the phenomenon, the flow physics, and its related effects. So in any CFD, we start with the generalized discretized form, a generalized equation for a scalar phi, and then we go to the continuity equation that has to be satisfied every time we solve the generalized equation. And for taking care of the fluctuations and turbulence, we have averaged the Navier-Stokes equation, which is popularly known as the Reynolds average Navier-Stokes equation. This gives rise to an additional term called Reynolds stresses, and for closing this, we go for a turbulence model. The turbulence model we use here is an explicit algebraic stress model, which is quite powerful in predicting many problems that has medium turbulence to high turbulence within the scope of runs. So this is the computational domain. If you look at the computational domain, the rudder that is placed in the computational domain, and the boundary conditions imposed on that is specified here. So we have the inlet with inflow conditions, the outlet with outflow conditions. The top condition has slip. The sides also have got slip. Rudder is a no-slip wall. That means the boundary layer is considered. Similarly, the bottom is also a no-slip wall. So a boundary layer is considered. So the interaction between these two boundary layers gives the complexity of the problem and the effect of bottom on the rudder. So the domain extents, which more or less we follow the ITTC guidelines, and we fix the domain extents as that shown in the second figure. So from the inlet, we put the center of the rudder with one chord length, and from the center of the rudder to the outlet extent goes to 10 chord lengths of the rudder. So this is the gridding we typically adopted, because grid plays a very important role in any CFD simulation. You spend most of your time gridding because the gridding and the boundary conditions take you close to a physical problem. So when you do such a grid, we thought that because there are so many rotations happening, there are different rudder angles that is being the rudder is being subjected to. So we went for an overlapping grid, and the biggest challenge was to choose the y plus value or the minimum grid size. For that, we had to resolve the boundary layer using the Blasius flat plate theory. So the Blasius equation was used to calculate the boundary layer thickness, and the boundary layer thickness was finally resolved. And we conducted a grid independency analysis, which gave us 2.9 million cells as the optimum cell. Though, of course, as sir asked previously, a higher grid size gave us better value, but we look at the difference between the values and the kind of computational effort we are putting in. We thought we should go for not 3.2 but 2.9. So this is a mathematical representation of the boundary conditions. So all the Dirichlet and the Neumann boundary conditions are clearly listed here. That was otherwise called a slip, no slip, velocity, outflow, and all those are mathematically represented. This goes into the governing equations which were already discussed. So this is the solver setting, typical solver setting. We use the shift flow solver, commercial solver with its XTAP module, that is the viscous solver module for capturing the flow. So we went for a steady incompressible RANS solution, a finite volume method with structured grid, then fully coupled velocity and pressure. And we also use it for for time advancing, which uses a quasi time advancing, but though it is steady, using this the alternating direct implicit solver. And the computational facility we have at the campus, we used that is a 32 core 256 GB RAM system with two licenses of the Shiflow solver with 16 core permissible limit to each. So we had an overall of 13 depth cases, and each case had to be run for 7 different angles. So we had a total of 91 simulations to run for this simple study or the introductory study. So these are the typical animations of the flow around the rudder. You can see the bottom interactions, the interaction of the rudder with the bottom coming more and more prominent when the angle is high, the drift angle is high, I mean the rudder angle is high, and also when the ratio, the depth to the rudder span ratio is very small. So this is one typical case for 6 different depths. This gives the next different depths, and when we have h by s 3.28, we are more or less in a deep water case. So you see that very less interactions happen there. So there has been a drastic difference from what we started with h by s 1.46 and what we have at h by s 3.28. So this is typically the flow separation. If you look at the lowest, shallowest water depth at 0 degrees, it's a uniform pressure distribution, but you have a lot of flow separation happening at 1.48 at the highest rudder angle. You can see the blue lines indicate blue contours showing a low pressure region there, and with increasing h by s ratio, that is as you go to more and more deep water case, this effect becomes less and less pronounced. So this is a typical animation that shows the flow separation for different water depths we have carried out for different rudder angles. The last one is not excluded because it's typically a deep water case, and we didn't put this on the slides. And the next important aspect is a cross flow that happens across the rudder when it is under shallow water because of the velocity that's increasing in the underwater, I mean the clearance region, and there is a flow across the rudder. This cross flow has been captured through our CFD simulations, and these are the static pictures, and in these GIF images you can see that the cross flow at 1.48, that is the shallowest water depth, it is very prominent, and it becomes more and more prominent as the rudder angle increases. So this is typically the rudder force versus the rudder angle graph, which is very similar to the straight line test simulations we do. And this is the graph which we use, or this is the plot which we use to extract y delta from each case. So we see that the non-linearity has just built in. For 14 degrees, we don't expect to have great non-linearities because the real rudder stall angle happens at 35 degrees, nearly 35 degrees. But a numerical simulation using RANs has to be restricted to 14 degrees. Yes, we did beyond 14 degrees, but it gave us a drop in the lift because of the limitation of the RAN solver, because of its limitation to capture such high flow separation. So for our initial studies using RANs, we had to restrict our angle to 14 degrees. So I wouldn't say that we have been able to capture all the nonlinearities, but yes, we did capture some of the effects. So this is, though I said I could calculate the rudder moment from the rudder force, this is the stock moment, only to check that the stock moment does change sign, uh, or the stock moments do change sign because of an eccentric rudder stock for a balanced rudder. That is the condition we have assumed here. So finally, we come to the regression fit we obtain. The regression fit is a fifth order accurate this thing. We had to go for a fifth order thing because the non-linearities are missing, and for making it more accurate, went for fifth order fit, and we also made the rudder independent of its geometry and velocity of flow by non-dimensionalizing that with the first prime system 1. And we also have a non-dimensionalized rudder derivative fit. So we have the rudder derivative, rudder force derivative. We also have the rudder moment derivative from the relationship that was already discussed. So in order to conclude this work, the analysis shows that the rudder forces, particularly the hydrodynamic derivative y delta, strongly influenced by the water depth, the increased forces in shallow water due to the proximity effects and the cross flow nature. So the relationship between the rudder force and rudder angle exhibits a nonlinear behavior with the larger angles generating larger forces, especially in shallow water conditions. Such a regression fit provides a useful tool for both designers and operators for operating the ship in shallow waters. This is, of course, a tool for the right anticipation. But this work does have limitations. The limitations are the open water rudder, without considering the effect of propeller and hull on it, has been studied. But since I said it's an introductory study, this has been taken as a procedure for further developing this. The larger picture is developing the mathematical model for the entire hull, propeller, and rudder for shallow water navigation. Then the choice of a very narrow rudder angle, 0 to 14 degrees, because of the restrictions or the limitations we had on the RAN solver. And we have only considered the hydrodynamic forces. We have not considered the structural deformation the rudder goes through in shallow waters. So these matters will be accounted for in the coming work, in the upcoming work, where we move ahead from the RAN solver to LES or a DES solver. And we also study the structural deformation of the rudder in the slipstream because of this high complex flow and the forces coming on it. So that's it. Thank you. Thank you for this opportunity.
Most of the engineering what I studied, and we never studied engineering so deeply because we studied everything. We are jack of all fruits, whatever you call it. Most of the accidents on the ships happen in the shallow water navigation.
Yes.
But what you explained over a rudder, I did not get any feeling what you had to explain. What changes in the shallow water? All the computational calculation, y delta, and other forces that we understood. But two things I missed out to grasp from this presentation. In shallow water, how does the rudder behave?
The rudder
Number one,
behaves
I
sluggish.
give you two contradicting this thing. Number one effect, what happens when the ship is going into the shallow water? As the speed changes, squad changes. And squad plays a very havoc role which not of experienced master do not grasp. And that's why the accident happens. That's number one, squad effect. And what interaction it has on the rudder, if you can explain that part. Second part, as you mentioned, the rudder is a slipstream effect. It means if the propeller is working, rudder will work. If the propeller is not working, there may not be any interaction forces working on the rudder that will change the direction of the ship.
You have gotten me wrong, sir.
Okay,
The
please
rudder
go
works
ahead.
even otherwise. If the rudder is in a slipstream, it experiences some additional forces. Slipstream condition is when there is, because of the proximity, there's a suction effect created by the propeller on the rudder. So rudder experiences an additional thrust. So the problem becomes more complex. So of course, the flow to the rudder is focused because of the action of propeller, but the rudder does its own role despite the presence of the propeller because rudder controls the ship. I mean, rudder doesn't turn the ship. The ship is turned by the hydrodynamic moment, but of course, the rudder controls the ship by facilitating the hydrodynamic moment. And all these become augmented when the ship comes from a deeper zone to a shallow zone because the rudder and the ship and the propeller, they start feeling the bottom. So there is an interaction between the seabed or the riverbed and the ship and the hull that gives additional forces on that. So now the rudder has to be the same steering effect. It has to overcome a greater force. So the rudder is becomes slightly slow in response initially, which creates a problem with the anticipation. So if you look at the turning circle maneuver which Sir showed, the same ship, the same vessel, if it goes for a turning circle maneuver in deep water, the turning circle radius would have been smaller. Here, the turning circle maneuver is, the radius is larger because of the sluggishness of the hull and the the rudder to come out of the effect of the shallow waters. And if back effects are also there, the phenomenon is more complex. But I have only considered the open water characteristics of the rudder. I have not considered any effect from the propeller or the hull.
So if there is a square on the speed, the square increases as per the square of the speed. Right? Just to give you an example. Suppose my container vessel has a square at 10 knot of 1 meter. Right? So at 14 knot, the square will be,
Of course, it will be more.
it will be, of course it will be more, but it will be, lot of people do not summarize in the mind, it will be just about double.
Okay.
Square of 10 is 100, the square of 14 is 196. So it will be about double. So,
As a squat happens, yeah. So I'm
right.
sorry.
So what I'm saying, the people misjudge this square effect, and what effect does that happen is the one is of course the underkill clearance reduces, but what effect does it have on the rudder is not well understood, and that if your topic of the today was the shallow water effect on the rudder, I did not get that answer. So
I think
Here
she has
I
only dealt with rudder. She hasn't actually dealt with spot.
not square, but the rudder.
She has dealt only with rudder
The
in
shallow
open
water, what happens with the rudder, that is not
as a rudder traverses through different water depths. So how does the rudder derivative become dependent on the water depth is my topic of today's presentation.
And she has already explained when you see H to T ratio,
H-
H to T
yeah.
ratio is shown separately. So the
That
effect
is CFD
change in
ratio.
H T ratio was
It's
augmented
a
as
though
the H T T
yeah.
ratio was changing. So the effect was increasing. That is what we are
Yes,
saying.
as the H to by T ratio becomes lesser.
Another dimension, a complicated dimension. As you said, when the propeller is turning, when the ship is maneuvering in the shallow water, so generally people give movement of dead slow ahead or full ahead, etc. And then suddenly stop the ship. It means propeller stops turning. Okay. So there is a very less flow of water going across the hull in other direction, external ahead, external ahead direction. In that case, what is the effect of the rudder?
Rudder, sir, it gets a focus flow from the propeller
Oh.
that enhances the performance of the rudder, but still the rudder is working under whatever conditions you're saying. The moment you put your hand on the helm, the rudder is working. And the rudder is under the influence of so many forces. So, how many forces you have at that condition that influences the performance of the rudder? Rudder is operated through a different mechanism.
No, no, okay, okay. Let me, maybe that's why I
Maybe,
said,
maybe we will have a discussion
maybe I
later.
was not able to explain.
We will have a
No,
discussion, sir.
but just, okay.
Yeah, sure. Thank
Okay,
you.
so that looks like there is a lot of interest in the talk. Does anybody else have any quick question? Otherwise, can you keep it a little bit short, please?
Re- Regarding the fit, when you talked about what is the correlation or
Yes,
RSME
the
and other fit?
correlation, sorry, I've not put on the, on my thing, it's a 0.98. R square is 0.98.
Okay, because what I was asking is because it is a complex correlation. So are you in future looking about some new what do we say ANN models or something to study the things, or do you find that this fit is
No, this
good
fit
enough to
is good
good
enough.
enough to?
Yes,
Okay,
yes.
okay. Thank you.
Yeah.
Okay, I think in the interest of time, not in the interest of science, we'll uh, close this session. Is that, Professor? We close this session now?
Thank you,
Okay.
sir. Thank you so much.
So, thank you, Dr. Janardhan. Oh, yeah, then please stay back here. Okay. So, you giving or? Okay, may I invite on the stage Mr. Janaki Ram Reddy, please? The first speaker. And then we'll have Mama Jalil and Sohida. The next, Dr. Anuleka Majumdar.